Hello, class. Welcome to our next lesson in 8th grade Eureka Math. We're in Module 3 still. We're working on Lesson 4. Now, Lesson 4 has kind of a long title called the Fundamental Theorem of Similarity. We can just abbreviate that to FTS. Now, Fundamental Theorem of Similarity, what it means is this is basic ideas about similarity. This is just the basics of similarity. So we're going to learn about dilation. We're still working on dilations. We're going to practice more dilations, and we're going to learn about some of what mathematicians believe are the rules for dilations. Because some of the ideas we're going to talk about today, mathematicians use to find missing information. So it's the Fundamental Theorem of Similarity, or FTS. If that title scares you, don't worry. It's just a bunch of words. I will break it down and summarize it at the end of the lesson today so that it is a little bit more understandable. But you'll need pages 37 through 48. You'll also need maybe some different colors of pens or colored pencils to work with. You will also probably need a ruler today. And something you'll need today that we haven't used possibly yet for our math, lined notebook paper. Just one page of lined paper. And that is for the problem set today. Now, actually, because today's lesson is all about theory, and you know it's about theory because it says theorem, I'm actually going to do the entire lesson with you today. I'm going to do notes, examples, problem sets, even the exit ticket. We'll do together today so that we can explain how all that goes. But these are the notes. Hopefully, you've already started copying down the notes. The road so far, what we've learned about dilations, about how things change in size. Getting bigger, getting smaller, we learned about that. We learned how to perform dilations. You know how to dilate an object using a center, using rays, and using measurements. We also learned some of the properties of dilations. For example, that dilations map segments to segments and lines to lines, which means the shape of the figure does not change. The shape does not change, only the size does. We also learned that while lines and segments change in size, angle measurements stay the same. So the lengths change, angles stay the same. Just the lengths change. So those are a couple properties we talked about. Today we're going to connect those with some new learning. We're going to use dilations today to learn more about lines and angles. Using dilations today to learn more about lines and angles. So that's what we're doing today. Now today we're also talking about, like I said, FTS, the Fundamental Theorem of Similarity. And the Fundamental Theorem of Similarity, the FTS, basically says two things. And you can see that I left the two things blank. We have number one, we have number two. We will fill those in after we finish our notes today. So I want to discover what those are using our examples. So I'm not going to tell you what they are right now. We are going to discover them together as we work together. So those are your notes for the day. Hopefully you have them copied down and you are ready to get to work. So let's start by going to page 37 of our books. Page 37 of our book looks like this. It has this exercise on it. One big angle made of a couple different rays. It says in the diagram below, points R and point S have been dilated from center O by a scale factor of R equals 3. So here's center O, here's R, here's S, and the scale factor is 3, which you know scale factor means we multiply. So R gets multiplied by 3 to make R prime, and S gets multiplied by 3 to make S prime. Remember, and this is important, so I want you to write this down too, OR, this segment right here, OR times the scale factor equals OR prime. OR times the scale factor equals OR prime. That's what scale factor does. Scale factor multiplies how long things are. So how long this is right here gets multiplied by the scale factor 3 to make the new one, to make it longer. It makes it longer because this is bigger than 1. If this was a fraction, it would make it shorter. But remember, this equation works for all changes. The original, I'll write it down here, original times the scale factor equals the new image. The original times the scale factor equals the image. And that's also true over here for S and S prime. OS, this segment right here, times the scale factor times R equals OS prime. The scale factor changes everything. So this equation right here, the original times the scale factor equals the new image equals the prime. Important to remember. Original times scale factor equals the new. Original times scale factor equals the new. We have done that before, but it's very important that you have that memorized right now. In fact, we're going to use it right now to answer A. If OR equals 2.3, what is OR prime? Well, we're going to use this equation right here. OR times the scale factor equals OR prime. So they tell us OR is 2.3, and the question tells us the scale factor is 3. So 2.3 times the scale factor 3 equals OR prime. Now for this, I'm okay if you use a calculator, but 2.3 times 3 is 6.9, which means OR prime is 6.9. So let's label that on the diagram so you can see what it is. They told us OR is 2.3. OR prime, the blue line right here, that is going to be the scale factor bigger, 3 times bigger. That's going to be 6.9. So the 2.3 is this red section, the original. The new one is the blue, the new image. So OR prime is 6.9 centimeters. So we should also label centimeters right there. And we can do the same thing for part B. If OS equals 3.5, what is OS prime? Well, I'm going to use this equation right here. OS times R equals OS prime. The original times the scale factor equals the new. Now they tell us the original right here is 3.5. The question, remember, told us the scale factor is 3. And if we do the math, we should find the new. So 3.5 times 3, again, you're allowed to use a calculator, but I'll just tell you, it's 10.5 centimeters. The new one, OS prime, is 10.5 centimeters. That's 3.5 times 3. So let's label it so you can see this. Remember, they told us the original was 3.5, so this green bar is 3.5. But after the dilation, it grows 3 times because the scale is 3. So OS prime, this orange bar right here that I'm scribbling down, that is going to be our 10.5. So you see how the size of everything changes. We're not done yet, because if you look at page 38, it tells us to do something for part C. It says connect the point R to the point S and R prime to S prime. So let's connect those first. So that's where you need your ruler. Connect R to S right here. So just get your ruler, connect R and S, and just draw a line through them just like that. And then connect R and S, R prime and S prime. Draw a line through them just like that. So we connect the lines. That is what we did. Well, okay. What does it want us to do now after we connected them? What do you know about the lines that that contain the segments RS and R prime, S prime? So what do we know about these two lines that we just drew, these two black lines I just drew? Think about it. What do you know? What do you notice about those two lines? What is the relationship between those two lines? How can you describe those lines that I just drew, and hopefully that you drew on your paper? Hopefully you noticed, well, Mr. Baylor, those lines look like they do not touch. They do not touch. In fact, if they keep going forever, Mr. Baylor, it does not look like they will ever touch, which is the definition of parallel. So we can say the lines are parallel. That is the relationship between the lines. What do we notice about the lines? They are parallel. Okay, next, what is the relationship between the length of the segment RS and the length of segment R prime S prime? So now let's talk about the length of these things. So let me get my ruler out. Let's just do centimeters. And I'm going to measure RS. I'm going to measure between R and S. And so I'm going to be as precise as I can. From the middle of R to the middle of S looks on my ruler to be about 3.2 centimeters. So I'm going to label that. RS looks like it's 3.2 centimeters. Now let me measure R prime, S prime. Let me measure this one down here. And from the middle of R prime to the middle of S prime looks to me like it is 9.6 centimeters. You can see it's not down here, 9.6 centimeters. 9.6. So RS is 3.2. R prime S prime is 9.6. Let's write that down on for part D. RS equals 3.2 centimeters. R prime S prime equals 9.6 centimeters. What do you notice about that? What is the relationship? I'll give you a little bit of a hint. You should have known this was 9.6 after we found the 3.2. Why should you have known that? What is the connection between 3.2 and 9.6? Think about it. Think about how you could have known that already. Hopefully some of you have noticed that if I do 3.2 times 3, I make 9.6. But where did the 3 come from? Now, those of you paying attention will know where the 3 came from because we've used it before in this question. It's right here. R equals 3, which means if this is 3.2, 3.2 times 3 makes 9.6. This follows the same scale factor. even though we added these black lines, we added these. These were not in the drawing they gave us. We added them. But it still follows the same scale factor. And if you look, the scale factor is everywhere. 2.3 times 3 makes 6.9. 3.5 times 3 makes 10.5. 3.2 times 3 makes 9.6. The scale factor is everywhere. The scale factor is everywhere. So, and that is actually part of the fundamental theorem of similarity. This is why they had us do this. This is why they had us find the 6.9, why they had us find the 10.5, why they made us draw these lines and measure them to see that the scale factor is pretty much everywhere. So now let's add to our notes what the fundamental theorem, the two parts for the fundamental theorem of similarity. What we just showed using this diagram. What did we learn from this diagram? Well, the first thing we learned is that the dilation of a line creates a parallel line. The dilation of a line creates a parallel line, just like in the diagram, RS made, the dilation of RS made R prime S prime. This line got dilated, it made this line, so dilations of a line makes a parallel line. The dilation of a line makes a parallel line. That's the first thing we learned. We also saw in the diagram, in our practice, that every, and I mean every length in a dilation follows the same scale factor. Every length in a dilation follows the same scale factor. Everything, even ones that you add later, like we added RS and R prime S prime later, they still follow the same scale factor. The dilation changes all of the lengths, and it changes it by the scale factor. That's just what you have to know. So those are the two parts of the FTS, the fundamental theorem of similarity. A dilation of a line makes a parallel line, and every length in a dilation follows the same scale factor. Those are the two things that are important to know. Now you might be saying, why do mathematicians do this? Why would they know this? And the answer is it helps them find missing information. Let's go back to page 38 and look at the next part of the question, where it says, identify pairs of angles that are equal in measure. Well, this is how we find angles that are the same. Well, what do you mean? How do we, you might just be looking at this diagram and say, Mr. Farrell, how do we know what angles are equal? Well, this is where you have to use your angle rules from Module 2. Because in Module 2, you learned about corresponding angles. And now we have parallel lines. Remember, our black lines are parallel, and we have a transversal. So we have corresponding angles. So for example, this angle and this angle are equal because they're corresponding. And this angle and this angle are equal because they're corresponding. So you need to so in this module 3, you need to remember the definition of corresponding angles. Also, remember that we did talk about in module 2 alternate interior angles, which means because you know alternate interior angles, you know that this angle and this angle are equal because they are alternate interior angles. You also know that this angle and this angle are equal because they are alternate interior angles. We also learned about alternate exterior angles. Alternate exterior angles are opposite on the outside. So you know that this right here, this green one, and this green one are equal because those are alternate exterior angles. And this one and this one are equal because they are alternate exterior angles. The fourth type of angle you learned about were vertical angles. Vertical angles are also equal. So you know this orange one and this orange one are equal because they are vertical angles and we have parallel lines with the transversal. And you know that this angle and this angle are equal because they are vertical angles. So when it's asking which angles you know are equal, you actually know a lot. You can know a lot of the angles that are equal because we have parallel lines cut by transversals. So when it says identify pairs of angles that are equal in measure, you don't have to find all of them, but we did find a lot of them. And how do you know they are equal? This is where you just list vertical angles, vertical, corresponding, alternate interior, alternate exterior, angles are all formed when a transversal crosses parallel lines. So this is a connection between modules 3 and modules 2, where you still have to know your angle rules. So that's really 3 skills we learned today. We learned that dilations make parallel lines. We learned that every length in a dilation follows the scale factor. And we learned that we can use the FTS to find angles that are the same. So we learned dilations create parallel lines. Every length is changed by a scale factor. And we use the FTS to know what angles are the same. 3 things we just practiced, and that's the lesson for today. Now, we're going to take a little bit of a break. I want you to go back, make sure you're all caught up on your notes, make sure you're all caught up on the exercise practice, and then so pause the video, and when you unpause the video, you can come and we're going to work together on the problem set and the exit ticket. So take a little bit of a break, make sure everything's filled in, make sure you know what you're doing, and come back ready to work on the problem set. Class, hopefully you took a little break to kind of stretch, relax, and check your notes and check your work to make sure you're all caught up. Let's work next on the problem set today. So going to page 39 is the lesson summary, which is actually kind of just these 2 things I said at the bottom of your notes, just in different words. So you already have the lesson summary written here underneath FTS. So I'm just going to move on from that mostly empty page. The exit ticket right here is what we're going to work on last today. So I'm just going to put that on the back of my packet. Next, we have like 3 pages, which are just the homework helper. Now, the homework helper is going to be just like the problem set, but because I'm doing the problem set with you, you might not need the homework helper today. But if you listen to me do the problem set and you still would like another example or another ideas about what to do, come back and look at the homework helper. The homework helper is always valuable, especially if you want another point of view. If my words are not enough, use the homework helper. Homework helper goes on page 43, 44, and 45. It's a long homework helper today because there's some graphs and there's some explanations. So you can look at that later on your own if you want another review. But then going to page 47, we see the problem set. Now I know it's a lot of words, but let's just do one step at a time. That's why I'm doing this with you, because I know some of you, when you see all these words, you might just quit and say you don't even want to try. But I'm going to do it with you. I'm going to talk about it. I'm going to do it on the screen. And so we're in this together. Let's just take it one little piece at a time, and let's follow one step. So the first thing it says, use a piece of notebook paper to verify the fundamental theorem of similarity for a scale factor that is between 0 and 1. So this is going to be a fraction scale factor. So in our example right here, we saw what happened when the dilation made everything bigger. For our problem set, we're going to see if everything still works the same way when it makes things smaller. So you need a piece of notebook paper, something with the blue lines on it. And now we just have check marks. So let's do the check marks. Mark a point O on the first line of the notebook paper. Now when it says on the first line, it means on the first line. So just on the top blue line, I'm going to put a dot, and I'm going to say that's O. That's my center. Check mark, done. Next thing says mark the point P on a line several lines down from center O. So I'm just going to go like, let's say P can be right. Let's go here. That'll be point P. And then it says draw a ray, OP. So what it wants me to do is it wants me to connect OP and make a ray going down. So there we go. And then what's the next thing it says? Mark the point P prime on the ray and on a line in the notebook paper closer to O. So I need P prime to be closer to O on another blue line. So let's put it right. Oh, let's go right here. This can be P prime. Does not really matter where you put it. There's P prime. So P was down here. P prime is closer. That's how you know, by the way, the scale factor is going to be a fraction because P prime got shrunk. It's smaller now. Now it says write your scale factor on the top of the notebook paper. So now I need to figure out what my scale factor is. So this is where you kind of have to do math. Remember, so let's figure out what our scale factor is. Our scale factor, remember right here, we have the original OP times R equals OP prime. The original times R equals OP prime. Now what I'm going to do, I'm actually going to just count the lines I move down. Because if you look at this, how many blue lines did I move down for OP? So let's just, I'm not even going to get my ruler. I'm just going to count how many spaces. So I go down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So OP was 12 lines down. I don't know my R yet, but I do know that OP prime, how many lines down is OP prime? I go 1, 2, 3, 4. So OP prime was 4. So I know how many lines I moved for OP. I know how many lines I moved for OP prime, but now I need to find R, which is algebra. I need to get R by itself. What I need to do is I need to divide by 12. Because 12 divided by 12 is 1, and 1 times R is just R. But if I divide this by 12, I have to divide this side by 12 also. So R equals 4 divided by 12, which is actually 1/3 when you simplify the fraction. 4/12 simplifies to 1/3. So my scale factor equals 1/3. Everything gets multiplied by 1/3. So the P time was 12. OP was 12. 12 times 1/3 is 4, which is where P prime is. So that's how I found my scale factor. I measured P, I measured P prime, I used algebra to find R. So that is the second check mark I had to do. What do I have to do next? Draw another ray, OQ prime, and mark the points Q and Q prime according to my scale factor. So I need to draw another ray. Let's do it going over here. I drew another ray. And I need so I need the Q and Q prime. So let's do Q first because we should do the original first. So I'm going to do Q here. So here's Q. And the reason I put Q there is because that is 9 lines down. So if that is 9 lines down, so OQ is 9. When I multiply by my scale factor, Q prime is going to be 3 lines down. Because 9 times 1/3 makes 3. So P is 12, P prime is 4, and that is multiplied by 1/3. Q is 9, Q prime is 3, because that is multiplied by 1/3. So I'm using my scale factor. I followed my scale factor. So check. And then now I need to connect P and Q and connect P prime, Q prime. So let's connect P and Q. Let me use a different color. I'll use red. There we go. And let me connect P prime and Q prime, the images. I'll use blue. There we go. So now they are connected. So I did that. Check. Now it says place a point A on the line segment between P, Q, and draw ray OA. So I need a point A now on PQ. So somewhere in the middle, I'm going to draw point A, does not matter where. And then I'm going to connect O with A to make OA. So I draw another ray just like that. And then because this is PAQ, so this is P prime, Q prime, A prime is right where they cross right there. There's A prime. I know that is A prime because it's where the ray crosses the line I already dilated. So this is what your paper should kind of look like when you're all done. Yours might look a little bit different because you drew different rays than I did, and maybe you put P and Q in different spots. But we did that. So this is what your paper should look like, close to it anyway, when you're all done following the directions. You have OP, you have OQ, you have OA, and you have the parallel lines connecting them. Just like that. And everything follows the scale factor. Everything follows a scale factor. Because remember, P was at 12. P prime got multiplied by 1/3 to make 3. Q was 9, got multiplied by 1/3 to make Q prime, which is 3. So that is what we got. Hopefully you have that, and hopefully you are ready to start answering the questions about this right here. Part A, are the line segments contain PQ and P prime Q prime parallel lines? Are these parallel? Are the red and the blue parallel? Yes, they are parallel. Yes. How do we know? Because FTS tells us that dilation makes parallel lines. Now it's asking, are any of these angles equal in measure? So OPQ is right here, this angle right here. OPQ is right where the angle I'm pointing at. Is that equal to OP prime Q prime, which is right here? Yes, these angles are equal because the vocabulary word we learned in Module 2, these are corresponding angles. What about OAQ and OA prime Q prime? OAQ is right here. OA prime Q prime is right here. These are also corresponding angles. So yes, they are equal. OAP and OA prime P prime. OAP is right here on this side. OA prime P prime is right here. Those are also called corresponding angles, just like we learned in Module 2. OQP and OQ prime P prime is OQP is right here. OQ prime P prime is right here. And those are also corresponding angles that we learned about in Module 2. So all are equal because all are corresponding angles. For part C, which, if any of the following statements are true? Does the prime equal the scale factor times the original? Does the prime equal the scale factor times the original? Does the prime equal the scale factor times the original? Does the prime equal the scale factor times the original? All of these are true because FTS tells us all lengths are changed by the scale factor. All the lengths are changed by the scale factor. So the same scale factor R changes all of the originals. And if you look, it's the same scale factor every time. Finally, part D, do you believe that the fundamental theorem of similarity is true even when the scale factor is a fraction? So looking at this, we have a fraction scale factor. And remember, in our notes, it says, FTS says dilation makes parallel lines. Did a fraction dilation make parallel lines? Yes. Part 2, does everything follow the same scale factor? Did everything in this follow the same scale factor? Yes. So, do you believe that the fundamental theorem of similarity is true? Yes. Because parallel lines are made and the scale factor is everywhere. Parallel lines are made and the scale factor is everywhere. So this diagram that you made on notebook paper shows you that the FTS works when there's a fraction scale factor also, which is the only thing they ask you to do. So hopefully you notice that. Hopefully you were able to measure that. Hopefully you see that. Let's go on to page 48 and see what the next thing is. Page 48 has 2 questions on it. This time they did the drawing for you. It says, Caleb sketched the following diagram on graph paper. He dilated points B and C from center O. So here's the original down here. Here's B, here's C, here's B prime, here's C prime. Just so you can see it a little bit better. What is the scale factor? What is the scale factor? Well, remember the scale factor. Let's just pick a couple points. I'm just going to pick the B's. Remember, to find the scale factor, we use the equation that we talked about earlier. The original times the scale factor equals the new one, equals the prime. Original times scale factor equals the new. So for OB, how many lines does it move from OB? 1, 2, 3, 4, 5, 6. So from the center to B is 6. The scale factor is what we're looking for. How many spaces to OB prime? This goes 1, 2. So now it's an algebra thing to find the scale factor. 6 times something makes 2. Divide both sides by 6. 6 divided by 6 turns into 1. So that's how we get 1 times R is just R. And 2 divided by 6 is 1/3. So the scale factor, R, equals 1/3. Because 6, the original, times 1/3 equals 2, the new one. And now it says verify the scale factor with a different length of segments. So we need to show that the scale factor works in other places. Well, for this one, I'm going to use BC and B prime C prime. Because those are straight lines, it's easy to measure. BC, this one, is 9 units. So BC is 9. B prime C prime is 3. Does that follow the same scale factor? 9 times 1/3 equals 3. So yes, that checks out. That follows the same scale factor. 9 times 1/3 equals 3. For part C, which segments are parallel? Well, which segments are parallel? BC and B prime C prime are parallel because they will never touch. They never cross each other. Which angle, part D, which angles are equal in measure? You have a lot of choices here because you have transversal. So if I just want to pick one, I might say that this angle right here and this angle right here are equal in measure. Or you can say that this green angle and this green angle are equal in measure because those are corresponding angles. So you can say angle OBC and angle OB prime C prime are corresponding angles. Or you can find any other angles in the diagram. You can find alternate interior angles. You can find alternate exterior angles. You can use a different set of corresponding angles. Like here's another set right here. You can say that this pinkish purplish angle is the same as this one down here. Or you can say that this orange angle is equal to this orange angle. If you match the colors in that diagram, they are all equal because those are all corresponding angles if you match the colors. You just pick your favorite angles on the diagram. Pick your favorite corresponding angles. Question 3 on the problem set, same thing. Points B and C are dilated from center O. So this is, except for this time, BC is here. Here's B, here's C, and here's B prime, here's C prime. So this time it grew. So this time the scale factor is going to be bigger than 1. What is the scale factor? What is the scale factor? Well, remember, we use the same equation. I'm going to use the C's this time because those go straight. Remember, the original OC times the scale factor equals OC prime. The original times the scale factor equals the new. So this time, the original, how many lines to get to C? 1, 2, 3. So OC is 3. Scale factor we don't know yet. But what's OC prime? How many lines to get to C prime? 1, 2, 3, 4, 5, 6. So 3 times something makes 6. So you should know this is mental math. R is going to be 2. The scale factor is 2. Because 3 times 2 makes 6. R equals 2. There we go. Now for part B, if OB is 5, so this one here is 5, what is OB prime? So OB is 5. What is OB prime? Well, you know we just have to follow the scale factor. If the original is 5, we multiply by the scale factor to find the new one. So 5 times 2, OB prime is going to equal 10 because the scale factor is, this is 5. We multiply by 2. C, how does the perimeter of the triangle compare to the perimeter of how does the perimeter of the original triangle compare to the perimeter of the new triangle? So we know this is 5, this is 3, and this is 4. So triangle OBC, the perimeter is 5 plus 3 plus 4 is 12. Now the new triangle, the one that we dilated, OB prime, remember, is 10. OC prime we measured is 6. B prime, C prime, this bottom part here, is 8. So the triangle OB prime, C prime is 10 plus 6 plus 8, which is 24. And if you look at that, the original was 12, the new one is 24, which means, how does it compare? It followed the scale factor. And remember, the scale factor was R equals 2. 12 times 2 makes 24. Remember, FTS tells us that the scale factor changes every length. The scale factor changes every length. So perimeter measures length around an object, so the scale factor still changes it. And that was the answer to part D also. The perimeter also follows the scale factor. We multiply by 2 because the FTS tells us scale factor changes every length. That is the problem set. Take a minute to check your answers against mine. Go back and look at the video again if you need to. And then when you come back, we're going to work on the exit ticket together. So take a look at the problem set. If you need any help, send me a message, reach out. And then we'll look at the exit ticket when you are all caught up with me. That was the problem set. Hopefully you're all caught up. If you needed to, you went back and looked at the video again to remind yourself how to do it. Let's work on the exit ticket together now. Exit ticket was on page 41 of your book. There it is right there. It looks like it's a lot of what we talked about today. Here we go. Let's talk about it together. Stephen sketched the following diagram on graph paper. He dilated points B and C from point O. Answer the following questions. So here's B, here's C, here's B prime, here's C prime. So obviously, it grew. The new one is longer, so we know our scale factor is going to be bigger than 1 because the lengths got bigger. So what is the scale factor? Well, let's use the B's to find my scale factor. Now let's look at OB, and let's look at OB prime. OB, how many spaces is OB? 1, 2, 3. How many spaces is OB prime? 1, 2, 3, 4, 5, 6, 7. Okay, so now we're going to use that information to find the scale factor. Now remember, the new one, OB prime, equals the original times the scale factor. New equals first times the scale factor. So now that we know OB and we know OB prime, we're going to use algebra to find the scale factor. OB prime was 7, OB was 3, and R is the unknown. Now to solve this, you should know algebra, just get the R by itself. So we do divide by 3. 3 divided by 3 is 1. 1 times R is just R. But if I divide by 3 on this side, I have to divide by 3 on that side. Now, that fraction does not simplify, so just leave it alone. Just say R equals 7/3. That is the scale factor. R equals 7/3. It is okay to have a fraction scale factor just like that. You don't need to simplify it because it cannot be simplified. Next thing we need to do is verify the scale factor with a different set of segments. So let's find a different set of segments to compare. This time I'm going to use BC and B prime C prime. And we're going to see if those have the same scale factor. So we used OB and OB prime and we got 7/3. Let's use BC and B prime C prime to see if we also get 7/3. So BC right here, the original is 1, 2, 3. B prime C prime, 1, 2, 3, 4, 5, 6. Oh, that's 7 also. So I still use my equation. The new equals what we started with times the scale factor. New equals the first times the scale factor. Well, B prime C prime is 7. BC is 3. And R is R. Well, this looks exactly like what we did up here. In fact, we know it's exactly what it is because if I divide by 3, 3 divided by 3 is 1. 1 times R is just R. But if I divide by 3 on this side, I have to divide by 3 on that side. So I still get R equals 7/3. So I used the OB and OB prime, and I got R equals 7/3. I used BC and B prime C prime. I also got 7/3, which is not surprising. Remember, we learned the fundamental theorem of similarity. FTS means every length follows the same scale factor. So we should get the 7/3 for everything. We should get 7/3 for everything. Number 3, which segments are parallel? Well, looking at this diagram, the parallel segments, segment BC and segment B prime C prime are parallel. Look at them, they never touch. And how do we know? Because FTS says dilation creates parallel lines. Remember, it was number 1. Dilation creates parallel lines. So BC and B prime C prime are parallel because this was a dilation. A dilation made them parallel. They have to be parallel because BC was dilated. BC prime was dilated from BC. Because a dilation made this, it has to be parallel. It came from a dilation. And number 4, last question on this. Are angle OBC and OB prime C prime right angles? And how do you know? Yes, they are right angles. Yes, they are right angles. How do we know this? Well, look at them. Look, these are perpendicular. They are made by perpendicular lines and perpendicular lines hit at right angles. Made by perpendicular lines, and perpendicular lines intersect at right angles. So that is the exit ticket. Hopefully you know how to find the scale factor. That was the big lesson today. Can you find the scale factor from a diagram? Also, the other big idea today was FTS, the fundamental theorem of similarity. So you need to be able to find a scale factor, and you need the fundamental theorem of similarity. And remember, the fundamental theorem of similarity says dilation of a line makes a parallel line, and every length in a dilation follows the same scale factor. That's why it's important to be able to find the scale factor, because if you find the scale factor one time, the scale factor is true for the whole dilation. So these were the big ideas today. If you have any questions, please reach out and talk to me. If you need anything, please ask. Remember to take a picture of your exit ticket and turn it in on the Google Classroom. And I will see you for the next lesson.